Good afternoon, everybody, and welcome to part two of Arista's Service Provider webinar series. This afternoon, we'll be presenting our Service Provider Building Blocks webinar. So, just a couple of house rules to go through. The first thing is, if we could please remind you to only ask questions in the Q&A panel of Zoom, not the chat window. We won't be able to answer any questions in the chat window. And just a final reminder that next week, same time, same place, we'll be having a final part of the webinar series, Next Gen Service Provider Use Cases. That's on 14th of July. So without further ado, I'll hand over to my colleagues Alexi and Mike to take you through today's presentation. Thank you very much.
Thanks, James. Hi, everyone. So today, as part of the building block, we're going to discuss about the US software architecture and the feature innovation in the routing domain, how the silicon network processors that make things happen in the hardware make the routers really matters nowadays for a modern and next-gen network environment. Then we'll discuss about some of the interoperability and some use cases. And finally, over the software and hardware, there's obviously a lot of routing features that you need, but also the ever more important need of the telemetry for your business, telemetry, and also the automation for being much more efficient on your daily operations. So I'd like to just give you a brief overview of Arista, not as a going through the whole history of Arista, but just looking at the current position of Arista in the networking domain. For example, we are a leader in the first review here of the network hardware for SDN. And we always had a very good position in the Magic Quadrant from Gartner. Here showing on the top right as a leader and visionary. So this is the data center networking Magic Quadrant. However, what we have done in the last 12 years in terms of embracing new technology, developing innovation for the data center, and being a real disruptor and being in a number two in the data center, we are bringing the same disruption into the routing world today. And this is illustrated here in generically through networking with the 100 gig market specifically. So keeping aside all the low speed, 1 gig, 10 gig, but 100 gig, we are number one for the 100 gig, both fixed and modular delivery. So what led us to that success? So I want to discuss about these differentiators within Arista, our drivers and motivations to make us so successful. But simply, you might be used to be doing the same as you've used before in terms of network architecture, in terms of product. You need to do some routing. You get a router, and you might be thinking about a specialized appliance or just reusing some design as you had, you're familiar with some protocols, and actually that might have led to organization-wide, maybe to some silos, to some complexity. And what we'd like to position is maybe sometimes they are just simpler ways of doing things. And one of the first brick that we wanted to position in that in that construction of a next generation network for a service provider is the operating system. So Arista has got EOS, the network operating system that runs on our switches. E stands for extensible. And from the inception, what we focused on for delivering the operating system is quality. So high quality in EOS comes from multiple facets. And one of them is obviously the software developer delivering that quality. So that sounds obvious and simplistic, but yes, the developer writes the code, is going to write the test plan, write the set of the automation test, because we grind our code in some large data centers, automating all the tests. And if something breaks, that software developer is immediately engaged in fixing that code, as opposed to the issue being forwarded to a sustaining team that has got no idea what code does, what was the intent. So really, the original developer is responsible end to end because he's the one that understands best that code. That might sound simple. That's how it should always be, right? Well, that might not be the case. You can investigate. So additionally, in terms of quality, delivering EOS features is important because we want to deliver new features for our customers, to provide new designs. We want to increase the performance and make sure that we deliver on time. Yes, but that's not necessarily the most important. Our most important criteria for delivering the software is quality first. So a feature may slip. Our release date for a code train might be delayed because the most important is quality. The second aspect about that operating system, the software as a building block of a critically important network, is the internal architecture of EOS. So first we started with an unmodified Linux kernel. It might sound simple and obvious, but yes, many other vendors have got a kernel. Sometimes it's Linux, sometimes it's some others, BSD and so on. But the main differentiator is that it's an unmodified. You've got a plain Linux kernel where we've got all the selected packages. You can add your own packages in there. You can give yourself access to the kernel to enhance things. You can download your preferred management tools and extensions from your trusted repository. It's fully open for you to do more. Then the way our operating system works is that you've got different agents communicating with a NetDB. The NetDB delivers state changes to all the other agents. Let's pick one agent in that illustration here. If one agent is updating something in that central NetDB, then the NetDB is responsible for propagating that change to all the other agents, whether they are related to the hardware or some other features or management. Then there's no direct communication between that agent that originated the state change and all the other agents, which means that when something goes wrong, there is fault isolation. The issues are already contained, so it doesn't impact the NetDB, it doesn't impact the states in it, and it doesn't impact the agents. So for example, if one agent fails, it's going to restart itself. When it comes back up, it's going to retrieve its previous states. It doesn't have to reconverge everything. So the control plane is stable inside the operating system. None of the other agents were aware of what happened. The hardware has not been reprogrammed. So it's really resilient. We provide hardware abstraction. Sounds obvious. We always have to abstract the software, the hardware with the software. But what's unique here at Arista is that years after years, as we bring different network processors, complete different families from multiple vendors, and new ways of programming hardware, we always abstract that so that the operating system provide a consistent way of managing the network. And to the point that there's a single binary. It's not different file sizes for different platforms. We've got 50 devices, whether it's 1 gig, 2 gig, 5 gig, 100 gig, up to 400 gig, multiple 100 port or 400 gig. Then it's the same binary that you put on a USB stick on your file server, and that's a very easy software versioning management. The operating system is programmable at all levels, which means the hardware can be programmed because you've got hardware tables that can be directly programmed by the SDK, C++, Python, Golang. You can add extensibility to the Linux kernel. You can run bash command. You can run Python or Golang, Ruby directly on it. You can add your own preferred scripting language if you want. And with the SDK, again, C++ or Python or Golang, you can interact with the NetDB. You can create your own agent and to interact in real time with the same publish and subscribe model. You can register some state, program them. And then you also have the programmability with the protocols. You've got OSPF, BGP, so that's the control plane. And finally, the management plane with multiple APIs that we've got throughout from OpenConfig with RESTconf, NetConf, gRPC clients. We also have an eAPI that's accessible through JSON, HTTP or HTTPS, allowing to communicate with some DevOps tool. Or here, for example, Puppet, Chef, that can be installed directly in Linux kernel locally. And also the streaming, I'll talk more about it, but that's also an API to stream natively. So the conclusion of this slide is that EOS is a very robust, scalable operating system that makes it very suitable for a highly critical network environment. And we think is the best OS for a router. So continuing on that building block of EOS is critically important. I've mentioned the internal architecture, the culture and testing from the software developer. It's not just our developers working hard and me telling you we've got great quality. That culture comes from the very top. So illustrated here is Ken Duda, our CTO and founder of Arista, one of the founder, that dictates to its development team. We realize that quality is the most important attribute of EOS, of Arista, and we want to keep. So we have to ensure this is always our most important priority. This is not a nice to have or one of the most important, this is the most important. So Arista, as a big differentiator, is that focus on quality. And how do we measure that? How do I prove that to you? Well, as an example, we've got some anonymized data here from a customer whose estate has been growing in blue. You see the amount of devices growing and growing. However, the amount of the proportion of cases, attack cases, either for questions or software bugs or RMA, in red does not stay the same. It's not to the same proportion. It's lowering because as the estate grow, well, you don't have a big increase in cases, so the proportion actually gets down. Other representation of our quality is, for example, this Arista NPS, the Net Promoter Score, which is done, measured externally, and at a score of 76 is really world class, as well as the Arista overall rating at 9.2. And another way of measuring through public data is on the right-hand side. You've got illustrated here the security vulnerabilities. So that's public data. You've got a link under the graph, as well as a link on the Google sheet as well. This is public data. You can see circled in green the amount of CVEs recorded from 2014 till 2020, and further in the graph you've got some other vendor X who's got different operating system, and you can see the amounts of CVEs they have accumulated over the years, in the hundreds and hundreds. And not only the mere mass of CVEs, but more importantly, if you dig into the details, you will realize that some of them are highly critical. So it's not just a difference in the amount, but also a difference in the severity of these CVEs, which does lead to question about the software quality. So this is a practical example of how software quality does matter to you. There's robustness, there's reliability, the extensibility, the visibility, but also some here example directly impacted security. So we talked about the operating system here, EOS. Now, what I'd like to talk is about the hardware, how different applications in your network don't necessarily, can't always be satisfied with the same kind of hardware platforms. And inside a hardware platform, what we look at is the network processor, what you might know as ASIC. There are different ways of designing a chip. ASICs are application-specific integrated circuits, so they are designed from top down. First, you want to fit all the features that have been selected and cram them into a footprint, a silicon footprint. While merchant silicon, much like CPUs and GPUs, are designed from a ground up, where we try to fit as many throughput, as many high clock as possible, to, yes, giving up sometimes keep cutting some corners in terms of features. We might not get this or that features, but the raw throughput, the raw performance often overwhelms the competition compared with, for example, the ASICs design, where sometimes a merchant silicon that's designed from the ground up can exceed the performance of an ASIC, even if there is a one generation gap. So this is the level of performance that this design type can provide. And when we look at what's on the market, obviously, Arista decided not to design our chip, and we decided that for having the options of selecting a variety of chips for different applications, and also always getting the fastest, densest, the best price performance ratio in our product, as opposed to, oh, we design a chip, we try to recover our design cost by letting it slip a few more years in our product. Now we can refresh that very quickly and always provide you what's fastest and best on the date. In your routing environment, you might have never considered merchant silicon as being suitable. Traditionally, 5-10 years ago, it was seen as a poor man choice, because maybe it was used in a data center as a top of rack switch. What was it doing? Layer 2, while you needed hundreds of features in as a router. However, the market trend has been to the simplification of the network requirement for service providers, because due to the economical changes in how the revenue increases per user or not, and therefore the need for building a network in terms of capex that costs less, that requires some kind of convergence, simplification of the designs. So kind of dropping more and more features of the necessity, at least. While traditionally routers were just doing everything under the sky. And at the same time, because the merchant silicon is improving, is now following Moore's law, or even exceeding the speed of Moore's law for different industrial reasons, the amount of of transistors on the core has increased, and therefore the table sizes have increased. The raw throughput has increased, but also how rich the processing pipeline has increased. And therefore, it has been possible for merchant silicon to adopt more and more of these traditional classical routing features on board, to the point that nowadays, merchant silicon is capable of satisfying a large portion of service provider hardware requirements, while in a very long past, maybe couldn't even offer half of them. So what we've got on the right-hand side is, for example, in the Dune family of processors, a single chip, it's the Jericho chip, Jericho 2, is capable of supporting 12 ports of 400 gig. That's in a single chip, and over 2.5 million entries in the FIB in hardware. So the merchant silicon for service providers is there, and has been for a few years already, but the scale and the performance has always been increasing. As I was saying, while previously 10 years ago, when merchant silicon was rather more suitable for the data center switching, maybe because it didn't have all the MPLS features and full internet table scale, that has been put on board as technology advanced and is now available into the routing till the transport. So this is the point of this slide here. I wanted to highlight that it's not just switching and then routing, but also transport is now being covered by merchant silicon layer 1. So here is an extract of our portfolio with, on the right-hand side, all the products that have got some very rich hardware features, meaning we've designed them for some use cases where it needs MPLS, it needs a richer pipeline because it's got more decap and ECAP, more packet treatment required. On the left-hand side, These products are rather designed for a data center or some simpler use cases where there's less packet manipulation to do less packet treatments. So the use cases are, for example, NFV, hosting, just raw performance. And on the right-hand side, it's generally rich, but you've got a multiple silicon that are used from Intel Fulcrum to Barefoot Tofino chips to the Jericho family from the Dune slash Broadcom and so on. All that variety of platforms, fixed form factor and modular chassis are all run by a single binary, single operating system. To the point that I was mentioning Jericho 2, so the latest platform support in 2RU form factor, 38 terabit per second with 400 gig port. We've got the 7500R3 up to 230 terabit per second. And finally, the 7800R3, our biggest router that supports 460 terabit per second with 400 ports that can, at choice, stay as 400 or break out as 4x100. So the merchant silicon has got a disruptive impact in the routing world because it now provides the scale of the table, the feature set, and a very disruptive price point. Talking about disruptive price point, and as mentioned, I mentioned transport. So the classical 400 gig WDM, it's not old, it's still fairly fresh, but 400 gig DWDM costs approximately $100 per gigabit. Well, what you see here from this year and this quarter is the 400 gig ZR. So up to 120 kilometers length. ZR plus will be later up to 1000 kilometer. So the 400 gig ZR is an Ethernet standard that includes some of the WDM and transport specifications embedded. So that's going to slash the price by 90% on the price performance ratio to $10 per gigabit. Again, heavily disruptive. And here's a final example as an end-to-end solution for transport. You've got on each side a 400 gig switch. So you've got 32 port of 400 gig slots, either QSFP-DD or SFP. In this use case, because of the power envelope needed for the longer reach, we're showing here OSFP. So you can have 8 400 gig ZR SFPs, the 400 gig transceivers, with the fibers connected to that cable. That cable is actually a MUX, DMUX. So it's a passive multiplexer, receiving the different wavelength and multiplexing them onto a single fiber. And then it goes into the line system to reach up to 120 kilometer, the remote end, transporting 3.2 terabit per second with absolutely no tuning or manual setup. This is a plug and play solution that just works. So again, disruptive technology. The routing world, the service providers, the telco, transport is being disrupted. The traditional market players are disrupted by this offering innovative solutions based on merchant silicon. But on top of all that great software, great hardware, there are functionalities. Mike will be talking about some of these functionalities used in SP use cases. But there's a growing need for telemetry and automation to work together. This image that you recognize from the beginning of the presentation, on the left-hand side, you've got EOS, but now you should know a little bit how it works between an agent and an ADB. That's why I did spend a bit of time explaining that, because now what's happening, you can combine the monitoring and the programmability of the operating system. All these state updates sent by NetDB to the other agents can equally be sent to that streaming agent we call Termin ATTR, which is Terminator. You can stream through open standard to remote locations such as your own collector, think Kibana, Spark, Grafana, and so on, or to Arista Cloud Vision, which is a turnkey solution for collecting data. You've got the large-scale database on board, you've got the analytics engine, you've got a portal, and you've got some northbound APIs to allow you to either collect the data or have some programmatic interfacing with it for consuming the data. It can interact with some ticketing system like ServiceNow, with Ansible for config management. And so there's a lot of power in collecting that telemetry that comes with the same granularity and interactivity. So it is as interactive in the receiving as it happens inside the switch, inside the OS. For example, if something happens, well, let's say something does not happen for a month on some very stable network, ideally, you can imagine, then nothing will be sent. So as opposed to collecting information with SNMP and checking logs frequently, then you will, these polling are unnecessary. So they are consuming resources. On the other side, if something does happen 5 times in a second, then your polling will miss that completely and you will not have that information. So how critical is that streaming is because of the internal working of EOS. Those 5 events in a second will all be realized. We will all see them because they are all trigger based, and that will come to the streaming agent that streams them immediately. So you will receive, whether it's on Cloud Vision or a newer open source platform, you will receive those 5 events and you will have visibility. So it's becoming critically important now to have that kind of granularity in to have accurate telemetry, accurate visibility on what's happening in your network, because then you can work on closed loop automation. If you've got such or such event, then you can react to it. So this is illustrating the difference between the classical monitoring method where we've poll by SNMP, we send CLI command, and then we've got syslog events now and then, every few seconds. Here, the collectors receive the telemetry in real time, and because it's trigger based inside the switch, there's no polling. This is 100% accurate down to the nanosecond accuracy, granularity. As well, the orchestrator to do config management or to orchestrate the network can access the EOS with the many APIs we've mentioned before. Here's an illustration of what it could look like from a telemetry perspective with different metrics. And you have got a kind of a time machine where you can go back in time, several months before, and zoom in and see at that specific millisecond what happened across all my different metrics everywhere, and then specify some thresholds that you define it. If I've got this threshold here and that threshold and that event happened 5 minutes before, then and what? And you now have the capability of making accurate decisions with your automation tools based on that accurate telemetry data. I've mentioned Cloud Vision as a turnkey solution for telemetry and automation. You can receive that through all the open standard we are using, because all the data is streamed through open standard. So you can consume that through your custom solution based, for example, for the storage on HBase or Cassandra. You can have different message queuing system and then run different analytics and visualize it the way you want. Obviously, it's a turnkey solution that can help you to start automation right now while developing your own system in parallel. The streaming can happen to multiple systems at once. It's very low bandwidth, it consumes very low bandwidth. And later on, who knows, maybe integrate your own custom solution to Cloud Vision or move directly to your own solution. It's flexible, there's no lock-in. So as a conclusion to here on automation plus telemetry, I think they work very well together. And adding all that, APIs plus telemetry plus networking protocol, you can make some very intelligent network decision based on machine learning. So I've talked about the importance of the operating system for in your routers. I've talked about great hardware that really disrupts the market, and then telemetry and automation. And what I wanted to show you now is, we're going to continue with Mike, but we have the features for routers that you would expect and better. We have 2.5 million entries in the FIB and more. With some TCAM can be extended. The control plane is usually scalable up to 20 million or more BGP path, and 512 ECMP, and you've got all the control plane protocols you would expect, like EVPN, MPLS, and segment routing, and so on. But what I'd like to show you is a demonstration of how we managed to tweak and to innovate on merchant silicon to make do more than they could. So what it is I'm talking about here, I've got a router. So I've got the Arista 7500 or 4. I've got on that router, I've got a line card. It's an R2, so that's a Jericho Plus, and it's got 25 gig port, 100 gig port. What I'd like to show you here is the amount of scale I managed to fit in. Show IP BGP. I'm showing you all my VRFs. So this is my default VRF here. I've got multiple full feeds, pseudo full feeds nowadays, a bit more in this VRF. I've got another internet VRF here, which means that I've got 2 feeds here. I need to program several times the full internet routing table in hardware. I also have some customer VRFs, and again, that means more routes to program in hardware. So I've got more than a full internet routing table here, and a flow spec as well. So what I want to do is show IP routes summary to show you how many route entries I will need to program per VRF. So here I'm on my default VRF. I've got approximately 660K IPv4, and you can see the prefix distribution by prefix length. So the same for IPv6. I've got 42K and this prefix spread. But the same will happen for all the other VRFs. It's just to show you quickly. And what I want to show you is show run. We've got some configuration for optimizing the prefix distribution inside the hardware. So the hardware by design might not be supporting as many entries in the IPv4 routing table in the FIB. In the silicons that are designed for routers don't necessarily have a single hardware table. It happens that some simpler versions of processors, network processors for the data center have a single one, but often the more complex one have got multiple tables for fixed length, for LEM, longer equivalent. So here we've got multiple hardware tables. And what we do with that optimization command here, we're going to optimize some specific prefix length. We're going to optimize specifically the prefix length of 20 and 23. How do we optimize that? Well, we're going to take some of the existing hardware table. We're going to show here, show hardware capacity. And in all these routing resources, you can see I've got a FAC, I've got the different routing resources. I've got the v4 host routes. I've got the v4 LEM. I've got a lot of routes in there, and that specific resource is is highly utilized, as expected in a router with full internet routing tables and more. And what we do here with that optimized prefix length is we are reallocating some of these prefix length 20 and 23 in other places. Another optimization is that expand 1922. If I take the example of expand 22, what it does is going to break apart a given /22 prefix and create 2/23. You might think, what's going on here? You are creating more prefixes. Why are you doing that? We are trying to optimize and to save some space, aren't we? Well, yes, but because we've dedicated some new buckets, some new hardware buckets for /23. We actually want to take some of the /22 out of some places and reallocate them into the /23. I'm going to show you an example. I take a route that's fairly easy to remember, 1.0.132. Let me check .1. Yeah, it's there. So I've got a /22 here, and I'm going to double check. I've got my 5 path here. I'm going to check the routing engine. So the routing engine is what collects all the decisions to be made and to program. That's what wants to program inside the hardware. That's just before programming the hardware. This is the intended entries that is going to be programmed. And you can see that my route, my prefix here, has got some little asterisks and an arrow. It's got some legend here. So that route is going to be optimized. So I've got the fake entry. So it's going to be optimized, which means that, well, let's look how it's being optimized in the actual hardware, how it has been programmed in the in my field. So I'm going to run a show platform IP route and then put that subnet. So what I'm doing here is I'm going that straight into the network processor and extracting the current content, which shows nothing. I don't have that route programmed. And the reason why is, remember what I said with the previous entry in my configuration. I am optimizing. I am breaking apart that /22 into some /23. So what I'm going to do is show IP hardware. I'm going to so I've got my extension here. I've got my route there, and I'm going to show platform IP route. Was it a copy paste problem? So that is the entry that doesn't show anything because I've selected the optimization, but normally the /23, did I copy paste something with a problem? Here. So I've got all my next sub that I had originally. You can see this is a /23, and my second part of the /23, because it's the adjacent subnet, is a 134.0. That's my second /23 issued from that expansion of the /22 into 2/23. So here it is. I've got my 2/23. I've doubled my amount of prefixes, but because I had a dedicated bucket, I've been able to overall increase the amount of scaling into my routing table. So that was the expansion part and optimization of some specific prefixes. So now there's another part of that optimization, which was at the end here, compress 24. So in this instance, what I'm going to do is optimize and actually compress rather than expand. I want to compress it, show IP route, 199.7.52.1. I'm checking whether it's there. It's there's a /117. I don't want a /16. I wanted a /24. Yeah, that's my 24. So here I'm going to check the routing engine again, what it intends to, what it holds and what it's going to do with it. So show IP hardware ALE routes. That's the intended route. So we want to program in the hardware. You notice that it's going to be optimized, and notice the fake ID here, 4353. So 4353, we've got the different next stops there on the right hand side. And I'm going to check with show platform. I'm going to look into the actual hardware again. 199.7.52.0/24. So that's my prefix with /24. Again, I'm going into the hardware. I'm going to look into it. And again, I see nothing because it has not been programmed there. It has been optimized. So what happened exactly? Well, what you will notice with my 52.0/24 here is got the fake ID 4353. And if I change that, if I look here at 53, which is an adjacent one, that's 53, I also have the same fake ID. So what is happening indeed is both /24 are being combined. So instead of a 52.0/24, I'm going to look at the 52.0/23, which is a kind of summary for both /24s. And you can see here, both prefixes have been combined in a single entry as 52.0/23. They all have the same next stops. So it's all good and working. And again, that helps to extract some of the /24, reduce the amount of prefixes, but also put them into a different hardware table. And finally, what I wanted to show you is yet another optimization. Show hardware capacity. Let's look at those different tables we had earlier. So remember all these tables, some of them are quite heavily utilized. They contain a lot of roots, and we had different method of relocating. We've seen already the optimization. And this feature here, what it's going to do is going to provide some compression or suppression of different prefixes. The way it works is as follows. Often you may have prefixes of different length. If a prefix is included into a shorter prefix, meaning it's kind of a overlap, there's some overlap, and the prefix of a shorter length includes the longer prefix, and really the longer prefix doesn't really need to be included and to be programmed in the hardware if they have the exact same next hops. If the next hops are different, then the routing decision will be different. So it will not be suitable. But if the next hops are exactly the same, then there is no reason for programming multiple times the same traffic path. So what this is doing, it's suppressing the redundant prefixes, removing the more specific prefixes, and programming only the shortest one, those that englobes the others, does a summary. What I'm going to run the same command as I did just before, and look at the optimization that this feature results in. So here I had 707K, the result is roughly 500. I had 94% utilization in that specific hardware table. Now I've got 65%. Likewise for V6, it went from roughly 40K to 23K, and from 50% table utilization to only 8%. And likewise for the other tables. So really what I've shown you here is that merchant silicon gives some great capacity and features, but EOS, and here this is the flex route capability, adds a lot of routing features that innovate over the merchant silicon. So there's really a lot of software innovation in EOS that adds a lot of capabilities. So I've talked to you about EOS as an important brick of your networks because the software is critically important. Then the scalable platforms with very high speed, whether it's layer 2, layer 3 routing features, or also transport at disruptive price point and incredibly high throughput and density, as well as the monitoring, the telemetry, and the automation that can work together to make your operations work much more smoothly, becoming really efficient at building your network and operating them. So what I was planning now is to let my colleague Mike Furby continue, but since I've been head down in this presentation, I don't know whether there's any question from the audience.
Hi, Alexi. We do have a couple of questions, but I think in the interest of time, we'll save them to the end of the presentation. Okay. So we'll hand over to Mike.
Okay.
Oh, hello. Yes, let me just quickly switch the screen. So just share the screen as I do this. Hopefully, you should see a presenter view. So thank you, Alexi. And so I'll pick up here on the basis that we have the building blocks in place in order to provide some actual solutions for service providers to take advantage of. now that we understand the capability that merchant silicon-based platforms now have, such as those that we produce. So I'm going to run through the topic of convergence, first of all, starting with the application of cloud principles to service providers use case, and then briefly look at some interop, followed by some examples with references to an architecture, from an architecture perspective. So what we're saying here in this image is how we would propose to apply our software-defined places in the cloud architecture to other network types and realize the same benefits. And indeed, we saw this presented in more detail during last week's webinar, but I feel it's useful to remind ourselves that we are applying common building blocks that are proven in the cloud to many other use cases, as suggested in the network schematic that's shown here. And the thinking here is that with the functional and operational building blocks available in the solution, and a common and simplified architectural approach, we can help service providers achieve efficiencies, which in turn leads to cost savings. What we're talking about, things like a reduced mean time to repair and the use of automation for speeding up deployments, as well as reducing the errors which can occur on scale provisioning. And this also, improves network availability and leads to greater agility in terms of service scaling and service turnup. But there's also one more component that's important, and that's interoperability. And as much as we here on this side of the screen would like to see 100% based Arista networks, the reality is, especially in the service provider world, that we will enter scenarios requiring a level of interoperability. But on that, we do indeed have a good story to tell. But before getting to that, I just want to look at one of the long-term challenges that has faced service providers, and it still persists. And that is there can be many separate networks within any service provider network, different requirements, and sometimes operated by different teams. And convergence is a topic that's been discussed, and I've been discussing for a long time now, and as far as I can remember. And while some have been able to adopt a converged architecture, many have not due to the differences in technologies that we've had in place. However, now with the ubiquity of Ethernet, which has just about ensured that all of these access technologies have converged to that common transport layer, we can start to think again about convergence and actually whether we can achieve it. And to consider that, there's something else that we will see today in that we have converged to Ethernet, but it's not just that, it's also about the edge services and the transport underlay that must be there as well. And I'm thinking about protocols like Ethernet VPN based services, which now are able to address both layer 2 and layer 3 VPNs in a common approach. That might actually lead to us being able to replace some more complex and less scalable solutions, arguably solutions like VPLS, but be able to continue to support successful solutions such as BGP layer 3 VPNs. And these services could be delivered on an Ethernet fabric style architecture, as suggested again in the network schematics that are shown. And this is where we can leverage on industry best practices that we've learned in the data center and the cloud by bringing these functions that were developed on our systems that were developed initially for those arenas. And we can bring those into the service provider market and now present new options to potentially achieve the convergence that has eluded many to date. And so on the question of whether true convergence is possible, I'll actually be as bold as to say that the answer is yes at this time. So given that assumption I've just made, I'm just going to take a quick look at some use cases and reference designs and interop. So quickly on interop in general, and while this is a little bit of a repeat from last week's session, but I'm going to just put a slightly different angle on it. So this is an industry event that we've taken part in the last 4 years, and it's the EANTC interop, which is actually part of the MPLS World Congress event, which is absolutely a service provider focused event. And in essence, the EANTC is a set of vendors all coming together to agree and then deploy multi-vendor test cases for demonstration and then reporting. And the idea being mainly to replicate new generation solutions, such as EVPN-based VPNs, and to prove that they work across multi-vendor implementations. And of course, there is an assumption here on the support of like common protocols, whether it's multi-protocol BGP and LDP, and that they are interoperable. So the bulk of the preparation itself goes into the interop of newer generation solutions that could be adopted as alternatives to existing solutions And indeed, as well as that, there's a lot of focus on SDN controller integrations as well, which we need to be able to demonstrate. So this is, it's a big event. It takes a lot of resources. It takes about 6 months to complete end to end. But we come away from this, confidently able to claim compliance or interop. And indeed, you can download the full report on this from the ENTC website. Now, I'm going to show a use case here. And although we're covering use cases next week, I'm just going to talk about this more in terms of reference design and interop, because a telco cloud is really a data center solution, as you can see suggested in the diagrams actually. And so in terms of the design itself, we would propose to approach this from the same perspective as we would a standard data center solution. That is something like a 2-layer spine leaf fabric based on Ethernet, and it could be either layer 2 or layer 3 IP fabric in the underlay, using well-known edge solutions such as multi-chassis lag or something newer like EVPN multi-homing. Again, data center principles we were applying to a service provider use case. And again, since the fabric is open standards based, then interoperability is also available for other vendor switches and edge routers, because in the end of the day, we need to be able to connect these services to the end users. And this will be achieved in this particular use case via access backhaul and into the core and off to the internet. And so once again, we're applying cloud principles here to the service provider use case in a field, obviously in data center and cloud, where we saw earlier in the Gartner quadrant that Arista is a leader in. And it's also worth mentioning that merchant silicon platforms are actually capable of even more advanced services than you might actually realize. So for example, we do have a range of switches called the 7170 family, and it's based on a highly programmable forwarding engine, even more so than the Broadcom Jericho series. And it's possible to program these platforms to perform some of the functions that you would normally associate with a service plane, and deliver these in hardware and on the network fabric itself. And the way this is done is that we enable these advanced capabilities with programmable custom profiles. And it's actually been possible for Arista to deliver functions such as a wire speed carrier grade NAT function, or even server load balancing, and some level of subscriber service redirection as well, and actually achieving that in the service and in the switching layer itself, offloading that function from costly service functions and actually enabling a potential for centralizing those service functions as well. And indeed, these functions that can be found in the telco cloud, as I say, to be very clear, they can be actually delivered on the Ethernet fabric itself. It's one alternative method there. Now moving on to another use case, this is internet peering, and this is the example that is utilizing the ribbon fib scaling factors that Alexi showed us earlier in the building blocks. And it's also a use case that demands interoperability, since in many, perhaps most cases, the peering device is a third-party system. And in the peering space, which can include internet exchanges as well as private peering, and we can see several different BGP stacks in play at once. And it's in this use case, which is a true test of BGP implementation. This is in terms of like path selection process, multipathing, and support for the full routing table, as well as understanding all the messages that come from connected systems, peer-to-peer systems. This is obviously both in the control plane and the user plane. And with our fully open standard streaming telemetry support, we get a complete insight into the systems in real time, which we can visualize as well on something like our Cloud Vision portal. And after all, BGP peering is the main building block of the internet itself. So to be able to fit into the use case, we must have a very strong implementation. And even here, it might be interesting to consider a fabric style peering edge architecture. And though at this time, to be honest, we're seeing more interest in replicating what's already in place today, we like to be able to support sort of current architectures, but we also look to the future with alternative node architectures, and an example of which I will show you shortly. But just before I move on, just a reminder of some of the key data points here with a high scale RIB, 2.5 million entries in the FIB, and this is for V4 and V6. So we got support for the full internet table for many years to come, and that with massive density that Lexi mentioned earlier. We can fit like 36 ports of 400 gig in a slot, for example, 48 ports of 100 gig in a single rack unit. But in addition, there's key security features such as RPKI and BGP flow spec. This is about flow spec. I'm just looking at the time. I might just move forwards quickly on this one. And just like we have a solution here that's very important to the peering use case. And it's been tested in proof of concept. I've proof of concept tested it myself with customers, and it performs really well. So we would see this as a differentiator, the ability to deliver this capability in our merchant silicon platform. We believe this is industry leading. RPKI, a question that has been raised by one cloud operator recently is BGP safe? And they've gone on to actually create a website that names and shames operators in terms of who's adopting RPKI. I think the important thing to say here is that this is a component that we believe will become mandatory. And I know from my own conversations with service providers that most people are either actively deploying it now or looking to deploy it in the very near future. So it's good to know that it's a capability that we also have in EOS today. In this slide, I'm just going to come to the supernode concept, and this is an example of an innovation that I alluded to earlier in terms of new types of architecture, new types of node architecture. And what we're talking about here is several improvements, including convergence improvements in ISIS, meaning that it can scale higher than is commonly considered to be practical to date. And this type of solution, which is really represented in the bottom of that diagram, is like an alternative to the large multi-chassis based systems that we used to see in the market and that no longer ship because of their high cost and high complexity. However, they did address a use case, and that is how to scale to even greater numbers of interfaces without actually having to update the node itself. And so the supercore architecture here is a little bit different in that it applies cloud principles to single node scaling. And given that we know that data center fabrics are proven to scale easily, i.e. they are highly fault tolerant, simple to operate, it also makes sense to us to apply these to the core router use cases as well. And also it's worth noting that the work in the ITF is being followed and indeed repeated by multiple vendors, and we see implementations of those changes actually appearing in multiple vendor operating systems at the moment. And so probably the biggest thing is this will require a leap in thinking and to adopt this type of architecture, to move away from what would have been a single P router in a site to a sort of a multi-node cluster like this. And get away from all the built-in hardware redundancy that a single big system have, which I'm sure as many of you would have experienced don't always fail over as expected. And the other thing is in terms of scaling, if you need to add more ports to this type of architecture, you just add a leaf. If the core isn't big enough, you just uplift the spine. And it's open as well, so you can use multi-vendor equipment if you like. And then finally on my section, I just want to just conclude on an important aspect on security. So we have security features which are mandatory from network operators. Their security teams require certain security features, else we won't be able to deploy. So we have a lot of security building blocks in our systems, in our solutions, from capturing metadata such as flow data and TCP dump, from threat mitigation, as I discussed, flow spec, and obviously things like access control lists, which are all programmable via the API. And of course, a complete telemetry solution, which we can visualize with our CloudVision platform. So that was a quick trip through through the application of building blocks, discussing interoperability, and the use of sort of data center focused reference designs in service provider use case. So just quickly move to the conclusion. And this is just a reminder of Alexi's first slide, asking the question or suggesting there's sometimes a better way to do things. And really the message we want to give, we want to change that set of road signs we saw to this one and just keep it simple. And it's one of the key tenets of Arista solutions that we prefer to deploy simpler architectures with fewer protocols. And yet we achieve the same results by using the building blocks that we have available in our platform. And the building blocks are listed there. Quality, automation, telemetry, operational excellence, and of course, price per gigabit per second, and ease of operations for an overall better experience. And at that point there, I'd like to hand back to James and actually ask if there's any questions that have come up.
I do have well, there's a couple, but I'll just keep it to this one question, Mark, just in the interest of time. And it's just around the your slide around convergence and whether you're seeing operators doing this successfully in the market, whether we're still seeing functions sort of siloed off. Yeah,
that's a good question. I mean, I've personally been talking about this for quite a few years, and the reality is that especially the larger operators haven't been able to converge. In fact, there's even been I've sensed resistance to it as well. But smaller operators, I mean, this could be like at the tier 2 level, perhaps they are actually achieving a level of convergence. But one of the mistakes that sometimes is made is that they try to bring all of these different service types into one single physical node, the so-called God boxes that we used to see. And that leads to instabilities, complexities that are just difficult to manage. Whereas if you take a sort of a more data center fabric type approach, then you could potentially have a common Ethernet edge and achieve your convergence that way. So common similar infrastructure running similar protocols, but not necessarily trying to shoehorn everything onto one box, as sometimes the diagrams tend to suggest. So I think that's the reality. It's happening. I see an appetite to do it. It often comes up, but it's hard to get there. It's definitely hard to do it. It's probably easier in greenfield, actually. But anyway, hope that helps.
Yeah, great. Thanks, Mike. So I think at that point we'll wrap it up. If you could just move to the last slide, Mike.
Yes.
Oh, and then one more.
More.
Yep. So just thank you to everybody for your time and attention this afternoon. I hope you found that useful and interesting. And just a final reminder that we'll conclude our series next Tuesday on the 14th of July with next generation service provider use cases, where we'll be doing a deep dive into some of the ways we're seeing our customers implement Arista technology. So thank you again, everybody, for your time, and enjoy the rest of the week. Thanks a lot.